Um, okay, so let's first just make quick revision on what we did, what we did so far in this chapter, and what we are gonna do to finish it. Okay. So number one, the first part of this chapter, I told you if you have first order differential equation like this one, so this is the solution of the first order equation like this one. Okay. So you have here you have here tau actually equal to 1 over a, and this is a, whatever. So a should be given to you, u should be given to you. What is unknown here is x. Okay. So tau here is 1 over a. X, you have x of infinity. Here is actually u divided by a, or tau times u. X of 0 is the initial value. You have to find it, and then you can plug it in this equation. That's it. So if you have this differential equation, okay, you can solve it this way. That's number one. Number two, what I did last time, I studied the case if you have a capacitor this way and you have R, this is specific case, and you have a voltage source Vs this way, and then I used voltage. Kirchhoff voltage law, and the main idea is I need to get an equation similar to this equation because I already know its solution. This was the main point here. The main point here, I want to find equation similar to this one so that I can use it to solve this solution here. So if you're using R and C this way, and if you have voltage, if you have here, if you take Kirchhoff voltage law, should be minus Vs plus ICR plus Vc is equal to 0. And we already know that IC should equal to C dVc by dt. So I already know we have differentiation here already. Okay? So if I plug, all what I do, I'm gonna plug in this one here. After I plug in, so here I can find this dV by dt plus 1 over RC Vc should equal to Vs divided by Rs. Is that okay? So now if you compare this equation to this equation here, you can find actually X here. X is actually Vc, the voltage across the capacitor. This is X. This is the unknown. That's what I want to find. And this 1 over RC is A. That means tau is 1 over A, so tau now equal RC. Okay? And now this part here, this is U. So X of infinity should equal U divided by A, which is equal Vs. Is that okay? That's what we did last time. Today, what we want to do today is the same thing, but instead, I'm gonna repeat last lecture again, but this time I'm gonna use inductor. I want to study this circuit when you have a resistance and then you have inductor this way. So if you have a circuit like this one, or if you have a circuit that has an inductor, okay. So I wanna get the voltage across the inductor. I wanna get the current. So I wanna repeat everything I did before. Is that okay? So I'm gonna repeat everything I did before, but you have to consider the differences. What are the differences? The differences are in case of a capacitor, I equals C dV by dt. However, in case of inductor, as I explained to you before, V should equal L di by dt. You can see the difference, right? So here, I is the differentiation of V. Here, V is the differentiation of I. So that's why when I created this equation here, the differential equation here, the unknown was V. But this time the unknown should be I, not V. You got what I'm saying? That is why this circuit is not going to help me to do that. Because if you try to mix the same thing like what we did here, it's not going to work easily. So for example, let's let's try and just to convince you once a problem. So Vs, so here this one should be negative Vs plus R IL plus VL is equal to 0. Okay, and then this time here. But this time here, let me do it. So here negative Vs, and then you have R times IL, and then you have here plus the voltage across this one VL. But here you have V here should equal L di by dt. Okay, so you can use it this way, and now it becomes di divided by dt plus R divided by L. R divided by L times IL, okay, should equal Vs divided by L like this. Anyway, so you can we will try to find any equation, differential equation like this one to solve. But this time we're not gonna use you know from what I explained before. If you have a voltage source, something like that, it's easy to convert it to a current source, something like that. They are equivalent. You remember when we did something like that, we got north here, and if you have here R, this one should be R. You have here G, so the current here is actually V divided by R. So if I want to use this one in this circuit, it's the same thing if you use this one. So you can use whatever easier for you. I can use this one or this one. So here, in case of capacitor, it was easier for me to use this one V and R. But in case of inductor, we would prefer to use this one because this one will be easier. So I will show you how can you use it. Again, there is no difference if you use this one or this or this source or that source, because you can easily convert between them. So here. So here the circuit we will study it. If you have a current source this way, and then you have a resistance R here, and this here we have IS, a constant current source, and then if you have here, so I will if you have inductor this way. So what I will do, similar to what I did before, I will find a solution to this specific circuit, okay, and then I will get a formula so that when you have any circuit in the future, I have to make this circuit similar to this one and use the formula. Is that okay? That's what I will do right now. So here you have here IS. Here I'm going to put it I1. And then here you have IL. And the voltage here VL. Okay. So if I apply Kirchhoff current law, okay, so here IS should equal to I1 plus IL. And I1 is actually VL divided by R. VL is the voltage here. This is the voltage here is VL. Okay. So here this one is VL divided by R plus IL. Okay. And now, because this is inductor, you know that in inductor, VL should equal R should equal to L di by dt. So now this one should equal to L divided by R di by dt plus IL. This should equal to IS. Exactly. Okay. So now I'm gonna rearrange it to make it in this format. Has to be in this format. Okay. So if you do that, now you have di by dt plus R divided by L times I equal to R divided by L IS. this one. So if you compare this equation with this equation, it's easy. You can see that this one is A. So now tau is equal to L divided by R. That's number one. Remember, in case of RC, tau was R times C. I just want to show you, I'm going to repeat the last lecture, exact same thing, but you need to see the difference between RC and RL. Okay, so in case of RC, this is tau was equal to RC, but here tau is actually L divided by R. Okay, and now if you see what is x of infinity, it's u divided by A. This is, remember, this is u. This is u. So actually it should equal to IS. And this one is a steady state solution. This is the steady state solution. That means what it means? It means, look here, guys. What it means? That means all this current is gonna go this way. In a steady state. Makes sense? So you know x of infinity, this is a steady state solution. That means all the current here is gonna come here. Okay? Why is that? How? What about this one? Nothing will come here? Yes. Why? Yes, because as I told you before, if you have an inductor, if you have a capacitor, the capacitor in steady state is actually short circuit. But if you have an inductor in steady state is actually short circuit. So in steady state, this one becomes like a short circuit. So that's why most of the current will come here. That okay? So here x of infinity should equal to IS. So all what I'm going to do right now, guys, is I will just use the solution I have here right now to get I, and then once I get I can apply this formula to get V. Okay, so if you do that, you find I should equal to IS times 1 minus E negative T divided by tau plus I naught E is minus T divided by tau. Okay. In exams, I will give you this formula here, but I will explain how we got it. Okay. Again, similar to what we did in RC. Number one, in order to use this equation, I need to find tau, which is, as I told you, L divided by R. This is number one. Number two, similar to what I explained last time, to use this equation, I need to find I naught. So what is I naught here? I naught is the initial current here. So you need to find it. What was the initial current? Okay. Similar to what we did last time when I found the initial voltage. But this time we will find the initial current. That's it. If you have after that you have everything else, you can use this formula. Okay. One more thing, as I told you, we can. This is for I. In order to get V, you have this formula here, so you can differentiate. You can differentiate I here. You can differentiate this one. Okay, multiplied by L, and now you can get the formula V. V here. This I is the current in the inductor, and V is the voltage across the inductor. Okay, so V should equal to V naught E minus T divided by tau. Remember, in case of capacitor, it was I naught E to the power minus T divided by tau. Okay, but here it's V naught. So what is V naught? What's V naught here? V naught actually equal to R times IS minus I naught, which is actually the initial voltage here, which is, so here, if you have here IS, and then here in the very beginning, you have I naught here, so the current here is actually IS minus I naught. So here it should be V. Okay. Let me tell you the conclusion. So again, all what I do, guys, is that number one, you know this is a relation between voltage and current in case of inductor. I know that. This is number one. Number two, I know if you have a differential equation like this one, I can solve it this way. That's what I know. Okay. And then, and then for this specific circuit, when you have here current source, resistance, and then inductor for this circuit, I was able to use Kirchhoff current law in order to fit this equation that's exactly similar to this equation. Okay? And then that's why I can just use this solution easily. I can solve it using this solution. So conclusion, this is the final conclusion. If you have a circuit like this one here, okay, R, and you have inductor here L, if you have a circuit like this one, then here is for the inductor, I for the inductor should equal to IS, which is this one IS, times 1 minus E minus T divided by tau, okay, plus I naught E minus T divided by tau. So divided by tau. Okay? By the way, I can rewrite this one it has a different format where I can put I naught so here I can write this one in a different format. So I can say this one is IS plus I naught times 1 minus E to the power of T divided by tau. So they are the same. I just did some manipulation to the equation. They are the same. Okay. So as I told you before, for this format here, this one actually is a steady state solution. So this is x of infinity, a steady state solution. And this is the transit. This is because of the transit. Okay? So again, if you have this circuit, I can easily know what is I. Also, I can know V, okay? Because V is actually V naught E minus T divided by tau, okay? And V naught is actually R, this R times IS minus I naught. That's it. So if I have this circuit, I can easily get an I and V using this formula. And I explain why. Okay, because I got a differential equation and I solved it. Okay, guys. So similar to what we did before, in order to use this formula, I need to find I naught. That's exactly what I did last time. We need to find I naught. Okay. Also, if the circuit is not in this format, okay, I have to make it this way. I have to make it in this format. So for example, just an example, if you give you a circuit, something like that. So this circuit is not similar to this one. I have to make it similar. How can you make it similar? I should get Norton here, not Thevenin. Last time I got Thevenin because I calculated the solution for this circuit. So I need a voltage source and I need a resistance. That's why Thevenin can help me. This time, in order to get something like this one here, I need Norton. So once you solve Norton here, now it becomes in the same format of this one. Okay? Because I only know the solution for this circuit. So if your circuit is not like this one, you have to make it like this one. Okay, guys, any questions? If I wanna draw this two equation, they should look like this one here. This is the current. We start the current here from I naught. This is the initial current I naught, and then this current is gonna increase until it becomes equal to IS here. And this part is the steady state. Okay, this part here is the steady state, and this part is the transient. Okay, so if you look at the voltage, so here we start from V naught, and then it's gonna go down until it becomes zero. And, okay, you know when the voltage is zero, it's short circuit. Makes sense. So here it can show you it is really short circuit because the voltage is zero, and is a current here is all the current of IS. Makes sense, right? So here you have IS, you have resistance, and you have coil. Okay, so if everything goes this way, that means that means this one became a short circuit. That's why it cancels this one, and this is exactly what happens in case of steady state. Okay? Again, if you have a capacitor in a steady state, it's open circuit. If you have a coil, an inductor in a steady state, it is a short circuit. Here you know V naught equal to IS times sorry, IS minus I naught times R. Any questions? Yep. Again, nothing is new. What I did here is similar to what I did last time, but the difference is that last time I used this circuit, resistance and voltage, okay, and then capacitor. This time I'm using current because it's easier for me to do the calculation this way, okay. Here this one has some equation, this one has some equation, and everything else is the same. Okay? So let's see some examples on this one. Yeah, so that's what I explained here. You need how you can calculate this differential equation. Tau is equal R, L divided by R. Okay. Tau is 1 over A here, so that's exactly, and this is the final solution, the same solution I explained to you here. Where tau is actually L divided by R, okay? Because this is A. Tau is 1 over A, okay? So L divided by R. So this is, so here you need to use this formula for I. We have another formula for V. That's it, this is the final conclusion. If you have final conclusion, if you have a circuit like this one here, this is the solution for R, this is the solution for V for this circuit. Please, don't use this solution if the circuit is different. It's not going to work because I calculated for this specific circuit. Okay? So let's see, I think I have here, similar to what I did before. If you look at this solution, we have two parts here. This part, this part is, this is the impact of the initial current, okay? And here, because this part here is a contribution or impact of IS. So this part is because of IS, this part because of I naught. That means if I naught is 0, if it's the beginning, there is no current, so this part is 0, okay? And I can rewrite this equation this way. So that's what I told you. This equation can be written this way or that way, okay? It's the same, I just did some manipulation here. But if I write this way, you can see this is the solution, and this is the transient response, and this is steady state. But if I write this way, you can see this is the impact of the initial current, and this is the impact of IS. Okay. Anyway, so and this is how we draw it. Same thing as I explained. Yeah, here I'm making a comparison between both of them. So here in case of RC, we have R and C this way, and this was the equation we made. Equation BC equal whatever here, and tau is equal RC. But in case of RL, only R and L, okay? So here we are going to use current source this way, and this is the equation here, and tau is equal L divided by R, okay? You can see the equation is very close. So here, but here instead of V naught, I naught, okay? It's still here, it's minus T divided by tau. This one also minus T divided by tau, okay? Anyway, so in exams, I will give you this formula anyway, but you need to know how to use it, okay? And that's what I will do in the coming test. In the coming test, I will give you the formula for V and R. Same thing in exams, if for this circuit, I will do the same thing. Okay? So let's see how we can solve the circuits, okay? So for example, if you look at this circuit here, the switch here, I'm telling you, the switch is gonna close at time T. So the switch was open. Okay, the switch was open for a long time. In the very beginning, the switch was open, and then at time 0, we're gonna connect the switch. Okay, why I tell you this way? Why this is similar to what we did last time? Okay, just to be able to calculate the initial current, because here to use the formula, I need to calculate the initial current. So when this one was open, okay, for a long time it was open. What was the current here? It was open. So what was the current here? 0, because the inductor is not connected. Okay, so there is no current. So that means the initial current. So that means when you use this formula, I naught is equal to 0. Okay, I will give you another example where I naught is not 0. Okay, but for now, for this specific example, I naught is equal to 0. Okay, now at time 0, we're gonna connect it here, connect this one. This is a very straightforward. Why? Because you have R, you have IS, okay? You have L, you have R, L, IS, and then you have also you have I node. All what you have to do, just formula. That's it. You have IS, you have R, you have L, you have I node. So just plug in here, you can get I. You have another formula for B. Okay. So that's what I did here. So here, initial current is equal to 0. I have R and I have L, so I can calculate tau. Tau is actually L divided by R, and then I plug in the previous formula. Then I find the current is this way. So this is the current. You can find here it's a 4 because it was here 4 milliampere, as you see here. This is steady state solution. And this part is transit. After some time, this part is going to disappear because this is steady state, this is the transit part, okay? So that's it. So I have here relation between current and time. So here in this question, I'm asking you, what was the current in the inductor when it was 2 milliampere? Sorry, yeah, to reach to 2 milliampere. Okay, I have a relation here. This one gives me a relation between current and time. Sometimes I give you the time, I can tell you, after 1 millisecond, what was the current? You just plug in here with the time to get I. But in this question, I give you I told you I, how long is it gonna take, how long will it take for the inductor current to reach 2 milliampere? So here I'm gonna plug in here. I know I, which is still 2 milliampere, and then I need to find T. This one. You have equation, right? I give you one value, you can get the other one. Any questions? Very easy, just straightforward. Again, similar to what we did before. In order to use these equations, in order to use the equation you have here, number one, the circuit has to be in this format. This is how it should look like. If it is not, don't use the formulas. The formulas we have for this circuit. That's number one. Number two, you need to know IS, you need to know L, you need to know R. Also, you need to know the initial current as well. If you have these, just plug in the equation. Is that okay? If you draw it, you can see here, it's the very beginning. Here at time 0 here, the current is getting, it was 0 initially. The current was 0, and at time equal to 0, we close the switch. So the switch is closed at time is equal to 0. At this time, you can see the current is increasing until it becomes 4. 4 here is this one here. So you can see this one. So you can see here, in the very beginning, all IS is here. So at time 0, all the current is gonna come here. And then gradually, this current reduces, this current increases until this point here, okay, after transit. After transit, all the current come here, 0 here. Makes sense? Because this one becomes a short circuit. Any question? So if I ask you, what was the current here, okay, in the 1000 ohm after 2 milliseconds? How can you calculate it? First, you need to find the current here because you already have the equation. You can plug in the equation. You can put here T is 2 milliseconds, and then you can get I here. And it's, the current here is actually 4 milliampere, okay, minus the current here. Because all the time, Kirchhoff current rule is working all the time. So always the summation of the current here plus the current here always is equal to 4. But what happens, the current here is going to reduce gradually, and the current here is going to increase gradually until this one becomes 0 and this one becomes 4 milliampere. But always at any moment, the summation of the current here and the current here equal to 4 milliampere. Is that okay? Any questions? This was a very easy example because the circuit was in the standard or similar to the circuit I already that has a solution. I didn't need to do anything because it's exactly the same circuit. Okay. I think I have another example here. I think it's the last example. And no, I have two more examples. So let's see this example here. In this example, you can see the circuit is different. It's not exactly the same circuit. Okay. So that means I need to calculate in order to make it the same circuit. But let's see here. So you have a circuit, something like that. You have a voltage source here. You have another voltage source here. You have resistance. You have resistance. You have resistance here. Okay. And then I give you everything. So I give you L. I give you all the resistors. I give you the voltage source. You have everything here in the circuit. Okay. And then here, after being closed for a long time, so the switch was closed for a long time. The switch is open at time equal to t equal to 0. Okay, I always give you this information. I tell you for a long time it was closed. To calculate the initial current. Make sense? Okay, so here and then after that, so as you see here, guys, at time t, I like these two figures. Okay, now we have two cases. Number one, at time t equal to less than 0. Okay, which before I open the switch was connected, okay, this way. This circuit was something like that for a long time. So it was in a steady state. That means the inductor now becomes a short circuit. Make sense? So it was connected for a long time. The disturbance didn't start yet. The disturbance is going to start at time t equal to 0 when I open this. Okay. So here, when t is less than 0, now the inductor is at a steady state, so it has to be short circuit. So why I give you this circuit here? Simply because you need to find the current here, because this current will be initial current here. Make sense? So I need to calculate. I need to find the way to calculate the current here, and this current should be the initial current. Okay. Now, when I open the switch, as you see here, when I open the switch, this branch is cancelled because it's not connected. Once I open to this branch, it's cancelled. So now this is my circuit. The circuit is here. Okay. This circuit is not similar to the circuit I have. It's a solution, but I can simply make this one similar to it. But this is done. So now what you have to do to make it simple? What you have to do? Number one, for this circuit, you need to find the initial current. This number, the first step you have to do. Number two, you have to make this circuit similar to the circuit that I already solved. Okay, that's it. Once you put that, you can just you have everything plug in the formula. Okay, and that's it. Okay? So let's start with this one. How I can calculate the current here. Okay, for sure you can use mesh. But if you use mesh, it may be more complicated because you need to find two equations. Because remember, this is just a short circuit here. Okay, you can use mesh. I think node here is much better for me because I have only one node. So here I have only one node here. So using only one equation, I can find the current here. Okay, so here for this node, I'm gonna call this node V1. Okay, so if you apply Kirchhoff current law here, the voltage drop here, which is voltage drop, I already know the voltage here, okay, and I know R1. I don't know V1, okay. So here for this current, I'm gonna have only one unknown, which is V1. Same thing here for this one here, because I know V2, I know R2. So the current here, I'm gonna have only one unknown, which is V1. Okay. Same thing here. Okay. The current for the current here, you have, so that means only using one equation is gonna have only one unknown, V1. So I can get V1. Once you get V1, okay, very easy, you can get the current here. Because the current here is actually V1 minus 0, the voltage here is 0, V1 minus 0 divided by R3. Okay. Yes, you can use mesh, you can make two equations here and here, but I think if you know them, it's going to be much easier. You need only to find one voltage here. Okay? Anyway, so let's do the equation here. So here, this is 0. So what is the voltage here? Negative Vs1, 0, and this one negative Vs1. What is the voltage here? Positive Vs2, because I'm moving from negative to positive. Okay, so positive Vs2, this one negative Vs1. Okay, so what is the current here? Okay, so the current here is actually so V1 minus Vs2 divided by, no, this is here. So V1 minus the voltage here, which is Vs2. So So at this point the voltage is V1. This point the voltage is Vs2. So V1 minus Vs2 divided by R2. This is the first part here. Okay? What about this one here? V1 minus 0 divided by R3, which is this one here. Okay? What about this one here? It should be, yeah, so this one was on here, Vs1 minus V1, okay, divided by R1. Okay, so here, yeah, because the current has to be, I think you need some direction this way. Anyway, so once you make this equation, you have only one unknown, okay. Then after that you can find V1, only one unknown V1. Once you find V1 here, it's easy to find R3. Sorry, it's easy to find the current here. Because that's what I'm looking for. That's what I want to find. Okay. So the current is actually V1 minus 0 divided by R3. So here you can see I found V1 is actually 15 divided by 4. Okay. And then in order to calculate the current of the inductor, so it's V1 divided by 5. Okay. I calculated it. I found it is 0.75. So that means before we open the switch, this was the current. This is my initial current. Okay. Remember, in case of a capacitor, you need to calculate the initial voltage. That's why I put there are some. This topic is exactly similar to what I explained before, but there are some differences. You need to consider these differences. Okay? So in the equation with the capacitor, I need to calculate the initial voltage. The equation with the inductor, I need to calculate the initial current. So this is the initial current here. Okay? So now I finished the first part. The first part I need to find the initial voltage. The second part now is I need so now after you open the switch this way, here I want to make this circuit to be this is the circuit, right? So now because this part we have to cancel this part. This part is not connected anymore. Okay, so I have to make this circuit similar to the circuit I already solved, which has to be a current source. Okay, to do that you have two solutions. Yeah, to do that, here this is the circuit I have. This is the circuit now. Okay, two resistors and then inductor. Okay, and when I make it looks like this one. So that means I want to convert this part to this part. Okay. To do that, you have one of two solutions. One solution, you can add these two resistors together. Okay, and now you know. Already from what we explained before, if you have here R and you have V, this one is exactly equivalent to a current source, and then here also R, but this one V divided by R. It's easy. If you have this one, you can convert to this one. If you have this one, you can go back to V. It's easy to do it this way. Is that okay? So in our example here, you have a resistor here, I think R3, and then I have a resistor here R2. And then you have a source here Vs, okay? And then you have here inductor this one. So the way you can do it, you can use this one here, or the other way you can do it, you can just calculate Norton here. Okay, if you don't remember this one, just do Norton here. Okay, so let me go back. Just want to make sure. Yeah. Okay. R2 and R3. So if let's do Norton. So for example, here you have here R3, here you have R2, and then here you have Vs, and then you have the inductor here. I want to calculate Norton to this part. Okay. So here for Norton, as you know, the first thing here we can do, if you calculate the resistance here, our Norton, I can make this one short circuit. Any voltage source, I can make it short circuit. So R Norton should actually equal R2 plus R3. Is that okay? If you want to calculate here, so here you have R3, you have here R2, and then you have here Vs, and then I'm going to make a short circuit here. That's what we do in Norton. So I need to find the current here, I Norton. Okay? You can see here I Norton should equal to Ps divided by R2 plus R3. voltage divided by the two resistors we have. They give you the current. Okay, that means now the circuit becomes this is IN and this is R node. Okay. It's exactly the same thing. Is that okay, guys? Any questions? It's exactly the same thing if you use this formula. So if I use this formula, now I just want to show you this is the same thing. So now I have here a resistor. This resistor actually is R1, also the R2 plus R3, and then I have a voltage source here, Vs. Okay, you know, so this one will give you current source and then give you resistor. This resistor is similar to this one, that will be R2 plus R3, and the current here, the current source is actually Vs divided by R2 plus R3. Okay, you have here R here is actually R2 plus R3. If you look at this one, it's the same thing like this one. So again, so all what I have to do here, I need to convert this one. So now, after I convert it this way, okay, so what I'm doing here, I'm calculating R Norton, as you see here. Also, I'm calculating I Norton. So after I do that, now this is the circuit I have, and I already have a solution to this. I have a solution to this circuit. So here we have IN here is actually in the formula, we call it IS. So if I go back to the formula we had, yeah, if you look at this formula here, guys, so this is the current in the inductor, if this is the circuit, so this is IS. Okay, IS is I Norton, just changes the name. Okay, and then you have R, and you have L. R here is R Norton, you have L. I know the initial current equation. So what after you do that, so now I have I. Same thing, we have another formula for V. If you want a V, you have another formula. So now, yeah, so here I'm gonna calculate I. We already have tau. Tau is actually L divided by R. This is tau 0.2. And then here you have I naught, that's what we calculated before. And then you have here I Norton, which is IS, which is 4 divided by 3. Okay, just plug in here, I get I. Okay. So here in this question, I'm asking you, so here I got I here, okay? So here, I'm not asking you for I. I'm asking you what is the voltage drop across R3. Okay? In order to calculate the voltage drop across 3, I need to find I, right? So I didn't ask you for I, but I need the voltage drop here. But to find the voltage drop here, I need I. Because once I find I, I'm gonna multiply it by R3. That's exactly what I did. So here what I did in the very end, once I calculated I, so this is I this way. So now the voltage V naught is equal to R3 times I, and this is the answer. So the answer here is not a number, similar to what we did before. The answer, it should have an equation like this one. It should E, and it should have T, I. Make sense? Any question? Let's see another example. Any questions? Okay. Let's see another example here. So here the switch is closed at time t is equal to 0 after being open for a long time. So the switch was open for a long time. I give you this information to calculate the initial current. So if you look here, the switch was open for a long time. Okay. At time 0, I closed the switch. So the switch was closed at time 0. Okay. So here, at time, look here, at time t less than 0, before we connect the switch. This is how the circuit is. Can you calculate? And number one, because this circuit in a steady state, the inductor here becomes a short circuit in a steady state. Number two, because the switch is open. Do you think this branch, I can remove it? Yes, because it's not connected. Very simple. Resistor is not connected. It's open, right? So so this part does not exist. Okay. So here, that means how I can calculate the current here? So that means very easy, right? Can anybody tell me how can you calculate the current here? The initial current? V divided by R1. That's it. So V divided by R1 because all the current is gonna come this way. This one is done removed. Okay? So that's what I did. So here is the initial current as you see, V divided by R1. Okay? So now I calculate the initial current. Is that okay? Yes.
So why would the initial current not be 0 since
That's a very good question. Why it's not zero? Because it's open. Simply because the inductor was connected in the circuit, it means in the circuit. What is open? The switch was open, but there was a current in the circuit going through the inductor. You understand what I'm saying? Yes, once I open the switch, the current in R2 is zero. That's okay. But still we have current here going through the, I care about the inductor. You got what I'm saying? So again, it's not always zero, it depends on the circuit. So if I go back here, in the first example, when the switch was open, the current here was zero, because the inductor was not connected. There was no current in this circuit, okay? But in this circuit here, when initially the switch is connected, so there was current here, so I need to calculate it. Now, the switch was open, but there was a branch. You got what I'm saying? It's a very good question. So yes, it was open here, but there was a path. There was a path for the current to go through the inductor. So it's not like switch always open, so no current. No, it's not like that. It depends on how you connect the circuit. Okay? So anyway, so now you have the initial. This is the initial current. Okay, I need it. Okay. Number two. Now we are gonna connect the switch this way. Okay, we're gonna connect the switch. What should I do now? I can't use the formula here. I can't use the formula because the formula I calculated, it was for this circuit. It had to be this way. So I have to convert the circuit I have right now to be similar to the circuit that I have its solution. Okay? How you can do that? So here, yeah. So here, simply I can get Norton. I can get Norton for this part. To convert or to convert the circuit from this circuit here to the equivalent circuit here, so that this one will become similar to the one we already have its solution. Okay? So anyway, so how can you calculate Norton to this part? Again, that's very easy. All what you have to do, number one, if you want to calculate I Norton, you have to make a short circuit here. You want to calculate, okay? Once you make a short circuit here, so this short circuit is going to cancel R2. Cancel R2. Short circuit in parallel to R2. You cancel R2. So all the current is going to come this way. Nothing will come here. All the current is going to come to this. So how can you calculate this current? Vs divided by R1. That's it. Vs, because all the current is going to come this way. Okay. Why? Because the short circuit is going to cancel this one. Okay. So the current here is actually Vs divided by R1. Very easy. Okay. So I Norton is Vs divided by R1. I calculated I Norton here. Okay. Now, how can we find R Norton? In R Norton, we have to short the voltage source this way. And then when you look here, when I look from here, can anybody tell me what is R Norton? Yes, R1 parallel to R2. Yes. Okay, that's it. So now, very easy. Now the circuit becomes something similar to the one I solved it before. Okay, after I got IS here is actually I Norton. Okay, R here, this R is actually R Norton. Okay, and then I have the formula here. I can simply use this formula. You need to calculate tau. Tau is L divided by R. I give you L. L is given to you. R is actually R Norton. This R here is R Norton. R Norton. Okay. Just here we call it I Norton, but when we calculate this formula, we call it R. It's the same thing. Here we call it I Norton, but in this formula I call it IS. Very small things shouldn't confuse you. Okay. So initially I call it IS and R. Here I Norton and RM. It's the same. Okay. So anyway, so now in order to use this formula, I need to find IS. Okay, IS is actually I Norton. I already found I Norton. I need to find tau. Tau is actually L divided by R. So R Norton. Okay. I need to find I node. We found the initial current I node. Okay. So after you plug in, you can easily find R. Can you find V? Yes, because V, if you just differentiate, V is actually L di by dt. Okay. So if you have I can differentiate it to get V. In exams, you don't need to do, you don't need to differentiate it because I will give you the two formulas. So if I go back here, when I calculated it, yeah, as you see here, guys, you can see here, this is the first formula it will give you in exams. You have IS, you have I naught, this is for the current. If you differentiate it, you get another formula for B, this one here. So to calculate V, I need R, which is R Norton. I need IS, which is I Norton. I need I naught, the initial current. We need R Norton. We need tau here. Okay? T divided by tau, or R divided by LT, whatever it is. Okay? So R Norton times L. So you don't. So you have one or two solution. If you have this one, if you have this equation, you can differentiate it to get this one here. Or you can just use this formula. I prefer just use this formula to get the voltage at both sides. Any questions? Yes.
On the last example we just did, there's not any current flowing through R2 even after you close it, right?
Okay, wait a second.
There would still be a short circuit in there.
Here, right? What's your question?
There's not any current flowing through R2.
Yeah, because this one was short circuit.
Well, even like in the original,
When you come here,
yeah, this L is still a short circuit, right?
this is an excellent question. Listen to me, guys. And it is one I found some students made this mistake, guys. Please listen to me. Let me go back here. When you here, in order to calculate Norton, I have to disconnect L completely. So I have to remove L. Okay, and then I have to make a short circuit just okay. So this circuit just to calculate I Norton. Is that okay? This circuit to calculate R equivalent. Okay. Once I calculate this circuit becomes like this one. So there's no short circuit. So this short circuit, it was in this circuit when you calculate I Norton. But that doesn't mean the short circuit will continue. It doesn't mean that. You understand what I'm saying? Because this is the way I have to calculate I Norton. The way you have to calculate I Norton, you have to make a short circuit and then you have to find what is the current through this one. Okay, but that doesn't mean this is the final. It doesn't mean this is the final circuit. You got what I'm saying? So that means here there is no short circuit here. Again, the circuit you are using to calculate V Thevenin, R Thevenin, I Norton, R Norton. Okay, this circuit should I'm making changes to the original circuit to be able to calculate some parameters like I Norton and so on. Okay, because even if this is the original circuit, sorry, yeah, this is the original circuit. There was no short circuit in the original circuit. I just added it. I removed. This is how we calculate Norton. I have to remove L, okay, and have to replace to put short circuit here. Okay, so this circuit doesn't mean this circuit is equivalent to this circuit. I didn't say that it's not equivalent. You got what I'm saying? This is the way you have to do to calculate. So this I just added this short circuit to calculate I Norton. Okay, but now what is equivalent to this one? This one here. I know. This one is equivalent to this. But I didn't say this one is equivalent to this one. You get what I'm saying? That's why I booked the short circuit just to calculate the current. But this one is equivalent to this one. I have to use this one. So there's no short circuit. Is that clear? I found students made this mistake in test one. Any questions? Okay, good. Okay, so this is the end of chapter 2. Well, I'm gonna start the chapter 8. Chapter 8. So chapter 8 is actually chapter 8 or topic 8. It's the same thing. So now topic number 9 is chapter number 10 in the textbook. That's why I call it chapter 10. So don't think there is a missing chapter. So this is topic number 9 with chapter 10 in the textbook. You understand what I'm saying? So we don't have chapter 9. Okay. We're not going to teach chapter 9 in the textbook, okay? But I'm going to teach chapter 10, which is topic number 9 in the course. Is that okay? First of all, how this chapter is different from what we did so far. Okay, so I will tell you what we did in this course so far. So this course so far, what we did in the very beginning of this course, we only consider resistance. If the circuit has resistance, also if the circuit has op-amp, or also if the circuit has a current source, voltage source, current source, dependent or independent, and then this is in the first maybe 1 to 5 chapters, I guess, or 6 chapters. Okay. So here, yeah, how can you analyze the circuit using this one? This is the first chapter. I explain Kirchhoff current law, Kirchhoff voltage law, Thevenin law, and so on. Okay, but the voltage source and current source here, they were DC. Okay, you know, when the voltage source DC, it can be DC or AC. The difference between them in DC, the voltage is constant, okay, with the time. This can be for the voltage, also current, the same thing for current. Okay, so if I tell you this source is DC, that means it is constant, does not change. In case of AC, no, it changes, but we're going to focus on sine waves. Okay, so this is how the current looks like. Same thing for the voltage, it can be sine wave. Okay, this is in case of AC. This is similar to the power we have here at home. This power is not DC. Okay, it is AC. But we still use DC. You know that small batteries, the small batteries you buy, these batteries are DC. Okay. Same thing, I think, for cars, for the batteries of the car also are DC. But anyway, so here everything we did here was the source was DC. And then after that, I started, last chapter is about how can you, if you have RC and you have RL, so RC and RL circuit, also the source was DC. Okay. That's why when the source is DC, any capacitor should become in steady state short circuit. Yes, there is some current in the beginning, transient, and then it becomes open circuit, and any inductor should be a short circuit. Okay. What I'm going to teach in this chapter and the coming chapter, next chapter, I just want to show you the difference between, is that what we have done so far? What I'm going to teach now is, if you have a circuit, this circuit has resistance, also it has capacitor, also it has inductor, okay? But the sources we have right now, sources are AC sources. That means can be sine waves, okay? You know, sine and cosine is the same thing, but shift is signal is shifting, okay? So it's gonna be sine signals, okay? So for the same thing for the current, okay? So that's what we do in this chapter. Next chapter we also will talk about, in this case, how can you calculate the power. So in this chapter, I'm not gonna focus on the power. I will focus only how can you calculate, similar to what we did before. I will give you a circuit. For example, it has a resistance, it has a capacitor, and then it has a coil this way, something like that. And then the input here is actually AC, not DC. Okay? If the input is DC and it is steady state, so simply, if I ask you to calculate the steady state solution, so this one becomes open circuit, and this one becomes short circuit, and that's it. Very, very easy. But now we're going to consider the case when the input is actually AC. How can you calculate the current here? How can you calculate the voltage here? In this chapter, I'm going to focus on the current and the voltage. Next chapter, it's the same case when the input here is AC. We are going to focus on the power. Okay. Again, when I say the input AC, as I told you, we're going to focus on sine waves because the power here at homes are sine waves. So what I want to tell you here, if the input is a sine wave, so all voltages here, all voltage and current also sine wave. Okay, and with the same frequency. Let me say it again. So here, for example, if the frequency is 1K ohm, 1K hertz, okay, so that means any voltage you measure, any voltage, any current we will, for sure, I'm gonna teach, some what I'm gonna teach in this chapter, give me a circuit like this one, but I just want you to understand the difference between what we have done and this chapter. In this chapter, we are gonna do something we didn't do before, about if the input here is AC source, and then you have capacitor, inductor, or resistors. Okay, how can you calculate the voltage? You need to find the voltage and the current everywhere. Instead, we are going to use Norton, Thevenin. Okay, we can use the mesh, approach or nodal approach, voltage nodal approach. Okay, but I'm telling you now, if the input is sinusoidal, okay, that means all the voltage and the currents here also are sine wave with the same frequency. With the same frequency. Okay? So these circuits don't change the frequency. Okay? So anyway, so the way we're gonna do it is so here you have a source. You have, for example, here capacitor. You have here inductor, this one. Okay. This is a circuit we have. We call this circuit. It is in time domain. Why is it in time domain? Because here the voltage source can be sine or cosine. For example, sine omega t. For example, okay. So the voltage source here can be sine or cosine, but this is a time domain. So what we will do is, instead of doing the calculations in the time domain, I'm gonna transfer this one to the what we call a complex domain. In complex domain, here, every source here, you have to convert it. I will teach you, that's what I will teach. If the voltage here or the current here in time domain, how can you convert it to complex domain? Okay. Same thing, how can you convert the resistors in this one to complex domain? So now I have a circuit. This circuit should be in the complex domain. Okay, it's not in the time domain, it's a complex domain. And then complex here means complex numbers. Complex numbers. So now the first step we will do is I will convert the circuit here from the time domain to the complex domain. Then I will do the calculation. Calculation, I can get V, I can get I, similar to what we did before. I will analyze the circuit, I will find into a complex domain. After that, you are gonna get I, but as a complex number. You are gonna get V as a complex number. And then I will teach you how can you convert it from complex to time domain again. Why you make it this way? Because the calculation, if you do calculations, the complex domain will be much easier than doing the calculation on the time domain. You understand what I'm saying, guys? This is the whole picture of the whole chapter. Number one, given a circuit like this one, I will teach you how can you convert this circuit from the time domain to the complex domain. This is number one. I will teach you how to do that. Number two, once you have this circuit in the complex domain, the calculation will be easy. And you still can use everything I explained before. You can use Thevenin, you can use Norton, Ohm's law, Kirchhoff current law, Kirchhoff voltage law. So you can use everything here in the complex domain as we did before. You calculate the current, you can calculate voltage. However, whatever you are going to calculate here will be in a complex number. Then I will teach you how can you bring it back to the time domain. And this will be your final solution. Any question? This is the whole picture, big picture. Okay? Any questions? Why you did that? Because I have one example to show you how, if you do the calculation in the time domain, will be too complex. It's much easier to do it in the complex domain. That's why before I start this story, I will make very quick, I will try to make a revision on complex numbers. If you have a complex numbers, how can you add them together? How can you do multiplication and so on? You got what I'm saying? Why? Because that's what we do here. You know, from complex number, we have J. J is actually the square root of -1. Is that okay? You know that. So that means if you have J to the power 0 should equal to 1. If we have J to the power 1 equal to J. If we have J squared, which is J times J, this one should equal to -1. If we have G to the power 3, so this one should equal to negative G. Is that okay? So these are all the values I can get. Any number after that is gonna go back to here. For example, if I calculate J to the power of 4, so this one will be similar to this one. Okay? J to the power of 5, so this one will be similar to this one, and so on. So it's gonna rotate again. So that's why in general I will say J of K plus 4N equal to J of K. So any multiple of 4, it have to be cancelled, because Jk plus 4N is equal to Jk times J of 4N. 4N is 1. You got what I'm saying? And K can be a number from 0 or 1 or 2 or 3. You got what I'm saying? So K can be a number 0, 1, 2, or 3. After that, you are going to go back to one of these values. Okay? So if you have J, for example, J of 20, for example, so this one should be equal to J, J5 times 4, right? Which is equal to 1. Because so let's have another number. For example, 21. If you have J to the power of 21, so this one should equal J1 plus 4 times 5. Anything 4 times 5, you just cancel it. So that means J to the power of 5. Okay? Why? Because J 4 times N, whatever value in any value for N, this one should equal to 1. Make sense, guys? So using this idea, you will find always we have one of these values. Okay. The other thing, any complex number, it can be A plus JB. A and B numbers, for example, it can be 2 plus J3. If you want to write it 2 plus 3J, I'm totally fine with it. There's no big difference. It's a J3 or 3J, it's the same thing. Don't be confused, okay? So any complex number, this part, this is the real part. And this is the imaginary part, okay? So if I wanna draw it, so this is here, anything real is here, anything imaginary is here. So this is 2, and this is 3. Then you have the point here, which is 2 plus J3. Okay? We still have 1 minute. Okay, so I can write any complex number. I can write it in this format here, and this form we call it rectangular form. This is the rectangular form. We have 2 other forms for any complex number. One is called polar form, which is actually angle theta. This is what we call polar form. We have also polar form, which is actually e to the power J of theta. Again, this is a complex number. This is also a complex number. This is a complex number. I can represent any complex number in one of these three forms. Okay. For this one, you have a real number plus J, and you have here the imaginary number here, this one. Okay. So how can you convert? So actually, what is in this graph? You already know when I tell you, for example, you have 2 and 3. So 2 is here, 3 is here. Okay. What about if you this is A? If I make a line this way, so this should be A, and the angle here is theta. Is that okay? So how can you convert if you have this is very important? You will know why. I can give you the number in this format, but in calculation, you need to convert this one. Or in calculation, you need to move from one form to another. Okay? I will show you manually how can you do it, but I think there are some calculators they can do it automatically. Okay, again, any complex number can be represented one of these 3 forms. You need to learn how to move from one form to another. Why? Why? Simply as I'm going to teach later, because some operation, for example, if I want to do addition or subtraction, it's easier to do some addition or subtraction if it is in rectangular form. But if I want to do multiplication or division, it's easier to do in this form. So that's why the calculation, you need to switch between, sometimes you need to switch between rectangular form and polar form. You understand what I'm saying? So if I give you the numbers in polar form, this way, it's easier to convert them to rectangular form and then do the calculation and then return it back if you need. Okay? I think some calculators can do something like that. You need to find it. But anyway, I'm going to teach you next time. Thanks.
is test two going to be the whole class period or just?
45 minutes.
45 minutes? Is there any way you can push it to Thursday?